we studied this voltage sensitivity. What did I actually here? Let's bring it down. Yeah, just now we studied voltage sensitivity is how much? 5 IV, and phi, phi is how much? NIA B by K. So we can write NIA B by K, and you have V here. So you have NIA B by V and K. Again, we have from Ohm's law, we can write NIAB by V equal to IR. So I get cancelled, and we have NBA by KR. And what is R? R is the resistance of the coil. This is the resistance of the coil. So this is the formula for your voltage and sensitivity, and we can increase voltage and sensitivity by increasing number of turns, by increasing magnetic field, by increasing the area of the loop, and by having a spring of lower torsional constant, and by having a coil of lower resistance. This is how we can increase the current sensitivity of the coil, or we can say moving coil in a galvanometer. So is it clear? This galvanometer, moving coil and galvanometer. We have only one participant. Let me put the bit. Okay. So let's take the screenshot, and then we can. Yeah. Is it clear? Okay. No response. Then, I know next topic here is, we can study if everyone present or not. Conversion of, or before any conversion, let's, take a question from, this topic, we just, completed this one. So let's try a, problem. We have a rectangular coil of area 5 into 10 to the power minus 4 meter square, and number of turns is 60 turns. 60 turns is about one of its vertical side. Okay, the coil is in a radial horizontal magnetic field of 9 raised to the power minus 3 Tesla. what is the torsional constant? What is the torsional, yeah, constant of the spring connected to the coil, if a current of 0.2 milliampere produces an angular deflection of 18 degree. Let's try this question. We have a rectangular coil and its area is given. Number of turns is given, and then see, magnetic field is given, and field is radial, means in horizontal direction. Now, we have to calculate the torsional and the constant and the value of the K. We have to calculate the value of K of the spring, and the current is 0.2 milliampere, and angular deflection of the coil is given to be 18 degree. So how much is the K? In equilibrium condition, what did you study? Applied in a torque is equal to the torsional and torque, that is in a K phi. And from this, we can calculate in a K as NIA B by NIA B by K. No, K we have to calculate by phi. It's simple, we have to just the question looks in a lengthy, but it is a direct question, You can just put the values now, and the number of turns is 60, current is 0.2 milliampere, and it is milli, so right here -3, and area is already given, 5 into 10 to the power minus 4 square meter, and then I area is given, a magnetic field is 9 into 10 to the power -3, and this angle is phi is 18. And what will be the unit here? Unit here. See, this is torque. No, this upper end term is what? Torque. And what is torque? You have studied this R cross F, R cross F, or if you write just in a magnitude, then it is in a RF and a sin theta. So you have Newton meter. Its unit is Newton meter. And this is, if you can take in degree, here we are taking in degree. So the value will be in Newton meter per degree. How much is the value? And you can just calculate this one. You can calculate it. I think the value is coming to be 3 into 10 to the power 9, -9, I think. So this is the torsional constant, and next topic will be next we'll be discussing conversion part, conversion of galvanometer into next topic will be conversion of galvanometer, galvanometer into 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 emitter. Now we saw the galvanometer, see, it can't, we can't measure any large values of current using galvanometer, because if you send a very large current, and torque will be very strong, and it can damage the galvanometer, So you can measure only a very small value of current, it can measure only very small value of current, value of current, in the order of a small value of current in the order of few milliampere, milliampere, only. We can't measure large value of current using a galvanometer. So we have to convert this into another device in order to measure large value of current, and so we are studying this conversion and how to convert a galvanometer into ammeter. So we saw here if the value of current is large, torque will be very strong and it can damage the galvanometer. So our objective is we have to allow small amount of current through the galvanometer, so that the galvanometer won't get damaged, and we should be able to measure the actual current, the actual current, So how to do that? Let's study. Suppose now we are representing a galvanometer by G, galvanometer by Z, and this is a galvanometer, and the current is I. Current in any circuit is I, and we have to measure the value of I. And then what we are doing here, we are applying a small value of resistance in parallel, with the galvanometer, and this is called shunt. Means in order to convert a galvanometer into ammeter, we are applying a small resistance called shunt is connected in parallel with the galvanometer. And why are we doing that? See, our objective is what? We have to reduce the value of current passing through the galvanometer, and we should be able to measure this current too. So when you apply a small resistance in parallel, then what happens? This I current at this point will split into two parts. Some current will go through the galvanometer, and some current, remaining current is I minus Ig. Remaining current is I minus Ig will go through the shunt. So you might have studied in a parallel combination, Suppose you have a parallel combination, this resistance is R1, this is R2, and if this is your current, and if current here is I1, if current here is I2, what is the value of I1? In this you might have studied, current, I1 means current through R1 is, how much? See, R2. If you have to write current in R1, current through R1, then in numerator you will take the value of resistance in the other balance by total resistance into current, and see the value of here, the value of this I1 will be small, if the value of your R2 is just small. So in the similar way, you have a parallel combination here. So the value of this IG current will be small if the value of resistance, this resistance, the resistance connected in a parallel is a small, means, here we have Ig equal to how much, we can write, yes by, similar way, yes, shunt resistance by energy into total current, and see here, the value of current through galvanometer will be small when your shunt resistance is small. That's why we take a small resistance here. We have very many fine concepts in these topics. So that's why we should understand why we are applying a small resistance in the parallel, and so by doing this we can our galvanometer won't get reflected because it will experience a small torque, and using this relation we can calculate the value of I this formula and some if you want to derive this one then what can we do here? See, in parallel combination, you have PD across galvanometer is equal to PD across the shunt. So what we can write, current in galvanometer is Ig, resistance is G, and current through shunt is I minus Ig, and your shunt resistance is, yes, let's save this one first. Okay. Yeah. Because we need some space. So, from here, with relation, you can also, no need to remember, if we have basic concept, we can write directly, and so if you want to calculate the value of shunt, then you can write Ig by I minus Ig, and then you have here I minus Ig, okay, and this using this formula we can calculate the value of shunt, and actually this Ig is the maximum permissible permissible value of current to the galvanometer. Means to how much should be the maximum value of the current through the galvanometer, so that your galvanometer doesn't get any damage. By taking this maximum value of Ig current, we can design the shunt resistance required. And we are almost done with this chapter. Next class I will just spend 10 to around 15 minutes for this conversion part, 15 to maximum 20 minutes, and after that we'll solve a few questions, and then we'll start second chapter, and that is magnetism and matter.